Hey guys, we're solving this chemistry paper today. This is 9701, paper 22, October November 2022. The last one in the series. So let's start by looking at the threshold first. So for paper 22, A was at 32, B was at 25, C was at 20, D was at 15, and E was at 9. Alright. So this paper was apparently harder than paper 2-1, or so it seems. Let's see. Okay, so the full mark is 60. A was at 32, B was at 25, C was at 20, D was at 15, and E was at 9. Okay, that's good. So yeah, it seems like 32 or the half, the midway mark was A apparently. So A star should be at around somewhere like 45 or something, approx. It's usually at the midway mark between A and full marks, or it might just be 6 or 7 marks above A. It actually depends on the percentile, the 90th percentile, on how students performed actually. So we're never sure really. They don't, disclose that. Anyway, let's begin. Question 1. Species such as NH3 plus, CO3 2 minus, and PO4 minus are examples of molecular ions. Okay, so identify the species. Ionic and covalent bonds both involve an electrostatic attraction between different species. So identify the species that are electrostatically attracted to one another in an ionic bond. So basically the cations and anions, right? So in an ionic bond, it's the cations and anions, or basically you could say that it's the oppositely charged ions. Okay, and in a covalent bond, it's basically the shared pair of electrons, right? And the two nuclei. This is really important, and this is in the definition of covalent bond itself. It's an electrostatic force of attraction between the shared pair of electrons and the two nuclei. Total number of protons, okay. So nitrogen has a proton number of 7 and hydrogen has a proton number of 1, so there are 4 in total. So that means we have 11 protons in total, and nitrogen has 7 electrons as well, and hydrogen has 1 electron. However, here one hydrogen is deficient, right? So we have 10 electrons, which results in a charge of +1. In carbonate, carbon has a proton number of 6, oxygen has a proton number of 8, so that's 8 times 3 plus 6, 24 plus 3, that's 30 protons, and here we just have extra 2 electrons, 32. Next, for phosphate, uh, well, let me bring the periodic table for you guys. It's gonna be easier for you. One sec. By the way, guys, if you like the content, please subscribe to the channel and hit the like button. It will help me a lot. The channel has been growing at a fast pace recently, which makes me really happy. Thanks for the support. Anyway, phosphorus, right? Phosphorus, yeah, it's 15. The proton number is 15. Okay. And oxygen, as usual, has 8 electrons, so that's 8 times 4 plus 15, which is 47 protons. And about the electrons, since it has a negative charge of 3 minus, there should be 3 more electrons than this, so we have 50 electrons. Great. NH4 plus is a Bronsted-Lowry acid. What is a Bronsted-Lowry acid? Basically, it's a proton donor. A Bronsted-Lowry acid, remember, anything that can donate a proton is a Bronsted-Lowry acid. Okay, so basically it's a proton or an H plus donor. When H4 plus is heated with NaOH, a pungent gas is produced, right, in ion equation. Fine. So NH4 plus and ammonium salt, if it reacts with an alkali, basically we get a few products. We get ammonia gas, right? We get water, H2O. Sorry, there shouldn't be a plus over here. And we basically get a salt. Okay, we get a salt. Now I don't know what the salt is. Like if it was ammonium chloride, we'd be getting a sodium chloride. That doesn't matter, it's a spectator ion. So if you want to draw the ionic equation, basically what takes part in the ionic equation? NH4 plus, essentially. Okay, it's going to take part. Now the sodium ion is actually a spectator ion because we can get rid of it on both sides. So essentially an OH minus or a hydroxide ion takes part in it, and it results in NH3 gas plus liquid water. They didn't include the state symbols, but you can if you want. Nitrogen atom in H4 plus is sp3 hybridized. sp3 orbitals formed from the mixing of 1s and 3 1 2s and 3 2p orbitals. Sketch the shapes of the 2s and 2p x orbitals. So guys, you know that s orbitals are spherical in shape, so you just need to draw a sphere on this side. This is the 2s orbital, and the 2px orbital is a dumbbell shaped orbital that actually passes through the x-axis itself. It acts like a skewer. All right, that's good. There are many naturally occurring hydrated compounds that contain the anion phosphate. Name the anion phosphate. Okay, so the name is phosphate, right? But you got to mention the oxidation number. So oxygen has an oxidation number of -2 always, except peroxide. So that's -4 into -2 is -8. So phosphate should be +5 if I want an oxidation number of +3. So this is phosphate 5 actually. Struvite is a soft hydrated mineral with Mr 245.3. The anhydrous form of the mineral has this formula. Calculate the number of molecules of water of crystallization in struvite, giving you answer to the nearest integer and show your working. All right, let's do this. So guys, what's the Mr of the anhydrous form? Let's find out the Mr of, NH4 MgPO4. So that's basically 7 plus 4, sorry, 14 plus 4. What's magnesium? 24.3 or something. Magnesium is 24.3. Phosphate is 31. 24.3, 31 plus 16 times 4, which is 64. 16 times 4 plus 31 plus 24.3 plus 4 plus 14. 137.3. Okay, that's good. Now, what about the MR of water? Not is it the MR of water. We know that the MR of H2O is 18. So we can basically find out how much from this hydrated salt, right? How much of this hydrated salt is composed of water essentially. So number of molecules of H2O is basically equal to the net mass 245.3 minus 137.3 divided by 18 basically. So 245.3 minus 137.3 divided by 18. 108 by 18 gives you an answer of 6. Okay, so you're getting an answer of 6 molecules of water. Great. OH minus reacts with 2 bromo 2-methyl propane in an SN1 reaction. Remember guys, SN1 reactions are for tertiary carbocations which proceeds in 2 steps. It's a first order reaction because the rate only depends on the concentration of the nucleophile. Here the nucleophile being hydroxide. Draw the mechanism of the SN1 reaction of OH minus with 2 bromo 2-methyl propane. So what is 2 bromo 2-methyl propane? 2 bromo 2-methyl propane. Mainly propane is CH2, CH3, CH2, CH3. This is propane. Now for 2 bromo 2-methyl propane, we just need the side chain as a methyl group over here on the second carbon and a bromine group over here. Fine. That's good. So what's the first step? The first step is the formation of the carbocation, right? The first step is the formation of the carbocation. So let's do this. This is del minus and this is del plus. So we need to show that there is heterolytic fission of this bond over here, heterolytic fission. So yeah, we got that. Now we end up with this. We basically get rid of the bromide anion and we end up with the carbocation. Now in the second step, basically the hydroxide, okay, the hydroxide anion, we can write like this. Fine, that's okay. They drew it in a weird way. You don't have to draw it like this. This hydroxide anion is going to attack this positively charged carbocation. Make sure you draw a curly arrow. And in the final step, we are going to get our product as, it's 2-methyl propan to all. 2-methyl propan to all. Fine. That's good. CH3 3COH. Basically CH3 3COH. Fine. So you need to show the dipole, you need to show the curly arrows, alright? Properly. We also get a byproduct. Like, remember, we lost a bromide anion here, and basically we also have an H plus. We get HBr as a byproduct, but we don't need to mention that here. Define tertiary bromoalkane. What is a tertiary bromoalkane? Basically, if you have 3 alkyl groups connected to the CBr carbon, that's a tertiary bromoalkane. Okay, so the CBr carbon is bonded to 3 other carbon atoms. Fine. So CBr, 1 carbon atom, another carbon atom, another carbon atom. Organic compound M forms when 2-bromo-2-methylpropane is heated with ethanoic acid. Okay. Draw the structure of M. Fine. Sorry, ethanolic OH minus. I just read ethanoic acid, my bad. So remember, if you use NaOH aqueous and heat, it actually gives a nucleophilic substitution reaction, but NaOH ethanolic actually gives an elimination reaction, right? So we had this compound, right? This one over here. After elimination, we actually end up with an alkene. Okay, so you can form the double bond on any side actually. Any side works. For example, I chose the right hand side. So this is the compound that we get. Is that fine? Hopefully this works. You can draw it like this, like CH3, CH3 like this, okay? That's fine. 17 marks done. Next question, it's on periodicity. So, by the way, if you do like the paper 2 content, please request more in the comments section. I've been doing mainly paper 1 because it gets the most reach. But if you guys want more paper 2, please comment below. I'll be sure to do more. So NaCl, you guys know that NaCl has ionic bonding. NaCl has ionic bonding. Its structure is actually a giant. You also know that all ionic compounds have giant structures. And the oxidation state of the period 3 element, basically as sodium, they're talking about sodium, is +1 over here. Fine. Now for aluminium, we know that the compound is covalent. In the mark scheme, they actually wrote or ionic, but I wouldn't actually go for that. AlCl3 is actually a covalent compound, okay? Now, about the structure, I think there's a mistake in the mark scheme. This is so weird. They're saying that AlCl3 has a giant structure. I need to check. I need to check. One sec, guys. Sorry about this. Basically, you guys know that any compound can never be completely ionic, right? You get to an ionic compound when the difference in electronegativity actually, exceeds a certain, difference. But aluminum chloride, we do consider it to be covalent because it does produce dimers Al2Cl6, right? Which does not actually form a giant structure. Okay, so um, here in this table, they actually told us to use C or I or M. But I understood why they gave ionic because aluminum chloride when dissolved in water in a hydrated state, it does basically form ionic compounds. You know the complex ion Al H2O5 OH minus. That compound is a complex ion actually. Anyway, so let's get back to it. So the bonding in NaCl is in fact ionic. The structure is in fact giant, and the oxidation number is +1. Now for AlCl3, the bonding is, I'm going to go for covalent, but in the mark scheme they also allowed ionic. And I think the answer should be simple, alright? It shouldn't be a giant structure. I will correct this though if I do find a mistake. In the mark scheme they wrote giant, as I can see. But it should be simple actually. Simple covalent compound. And the oxidation state is actually +3, right? In silicon, it's covalent bonding for sure. The structure is simple, right? And it should be +4 over here. It should be +5 over here. Simple structure, covalent, right? And here the oxidation number is +3 actually, and here the oxidation number is +2. Because chloride is on the right hand side of the group of period 3, right? So it has the highest electronegativity. So chloride should have a negative oxidation number, while the other should have a positive oxidation number. Okay, moving on. Right. Equations for the reactions of NaCl and PCl5. NaCl does not react with water, okay? What happens to NaCl though? It basically dissolves in water, okay? So this is what happens with NaCl. So NaCl solid, it basically dissolves in water to form Na plus aqueous and chloride aqueous. That's literally it. On the other hand, PCl5, it's a bit problematic. Why? Because it reacts with water. So you have to show water. Okay, I won't show you the balancing. I have it memorized. Basically, we end up with phosphoric acid, H3PO4. If it was PCl3, we'd get phosphorus acid. Here we're getting phosphoric acid, and we get HCl. So now to balance this, we need a 5 over here, right? We need a 5 over there. These are aqueous. And yeah, water is liquid. So we got a 5 over here. Now to balance this oxygen over here, we need 4. And yeah, that's more or less it. It's balanced now. 5 plus 3, 8. 4 to the 8. Yeah, that's great. So please memorize these equations. These are in your course book, alright? You can find them in your course book. Now, yeah, aluminum chloride gas exists at equilibrium with Al2Cl6 as shown. Complete the dot and cross diagram to show Al2Cl6, the dimer. Okay, let's do this. Okay, so here you go. 1, 2, 3, 4, 5, 6, 7. Okay, so we have another chloride over here, and another chloride over here, and aluminium over here. Damn, this diagram is so bad. Wait, yeah, no, it's gonna work. Okay, just a size match. Something like this, right? Yeah, let's go. Okay, and we copy this again. So in total, we have 6, right? Yeah. Okay, let's do this. So essentially, um, aluminium forms a single bond with three chlorine atoms. Okay. So, and on the other hand, it gets a dative covalent bond from another chlorine atom. That's how it works. So this chlorine atom will provide the dative covalent bond there. You get what I mean? And that's how it is. And here we just have typical single bonds. Okay, there you go. Hopefully I haven't missed anything. Oh yeah, single bond over here. So 3 single bonds and 1 dative covalent bond for each. That's how it works. Okay. State the effect of an increase in temperature on this. So it's an exothermic reaction, right? So the equilibrium will shift to the left. Sorry. So yeah, we are gonna get less of the dimer. By the way, you needed to show the state symbols, alright? Or else you wouldn't get marks. They mentioned that in the question. So let's explain. The reaction is exothermic, right? So the equilibrium shifts to the left hand side. So the forward reaction is exothermic. So the equilibrium shifts to the left. Fine. That's great. To the they said left hand side. Okay, fine. Let's just copy the mark scheme. Always try to copy the mark scheme, by the way. Like when I was a student back in the day, I mean, I still am, but not an A level student. Basically, I just wrote the mark scheme answers in my question paper, and I just read them later. Like when I reviewed the questions, I just read them. I tried to follow the mark scheme as much as possible. All right, so you guys should do that as well. So 3.30 gram sample of a pH3 chloride is heated to 500 Kelvin in a sealed flask. Okay. At this temperature, the chloride is a gas of volume 250 cm3 and pressure is 323 kilopascal. So let's use PV is equal to nRT to calculate the MR. Deduce its formula. Fine. So we know that this can be written as mass N can be written as mass by MR times RT. So MR is actually mass times RT divided by PV, right? So the mass is 3.30 grams. R is 8.31. Temperature is 500 Kelvin. It has to be in Kelvin, not degrees Celsius. The pressure has to be in pascals. So this into 10 power 3. And the volume has to be in meter cubes. So 250 into 10 to the power minus 6. So let's see what we get. 3.3 into 8.31 times 500 divided by 323 into 10 power 3. Wait, I messed up. 323 into 10 power 3 times 250 into 10 to the power minus 6. All right. We got a value of 169.8. Or basically 170, right? Now, okay, so basically what they did was they did this separately, actually, guys. They didn't do it my way. They did this. They wrote PV is equal to nRT. So N is equal to PV by RT. Or basically 323 into 10 to the power 3 times 250 times 10 to the power minus 6 divided by 8.31 into 500. So they get a value of N is equal to 0.0194. Then they just did this. You know that moles equals to mass by MR. So MR is equal to mass by moles, which gives us the same answer essentially. Now it's a period 3 chloride, right? 170. So let's check these ones, okay? So 170, if we try with NaCl, let's see. So Na is 23, Cl is 35.5. 23 plus 35.5 gives us an answer of 58.5. That's a fail. Okay, so 35.5 times 3 plus aluminium is 20 something, right? Aluminium is 27. That gives me a value of 133.5. So it might be silicon. So 35.5 times 4, and silicon is 32 point, sorry, silicon is 28.1. So let's add that up. Plus 28.1 gives me an answer of 170.1. All right, we have our answer. It's consistent with SiCl4. That's great. Perfect, guys. Okay, we're doing pretty good. Not bad at all. Let's move on to the next one. How many questions were there, by the way? Just 3 apparently. Okay, that's pretty good. So for this question, an excess of chloride is added to 1 cm³ of bromine. So chloride is basically chlorine. This is fluorine, chlorine, bromine, iodine. Uh, Chlorine is a stronger oxidizing agent than bromine, right? So bromine can't really oxidize chloride. Do you guys understand? To oxidize a halide, you have to be above it. Okay. So chlorine can oxidize bromide and iodide. Fluorine can oxidize all the 3 halides below. But iodine, sorry, cannot oxidize bromide, chloride, or fluoride. Bromide can oxidize I'm messing up. Let me explain again. As a halogen, you can only oxidize the halides that are below you. So iodine cannot oxidize bromide, chloride, or fluoride. Bromine can oxidize iodide but not chloride or fluoride. Chlorine can oxidize bromide and iodide but not fluoride. That's how it goes. So describe what is observed. Basically here we are not going to see any visible reaction. All right. So orange color of solution remains. Orange color of solution remains, or you could say that no visible reaction occurs. Okay, why? Basically because a bromine or Br2 cannot oxidize chloride. That's the gist. All right. Or you could say that, bromine is not a strong enough oxidizing agent to oxidize, chloride. Right. SCl2 has AMR of 103.3 and is a liquid at room temperature, but SBr2 has a AMR of 191.9 is a gas at room temperature. So it has higher AMR, but it's still a gas. Explain the difference in physical state to give you answers in terms of intermolecular forces. So SCl2 and SBr2, guys, how does it work? SCl2 and SBr2. So SCl2 and SBr2. What's the situation basically? So both of these are polar molecules. Okay, both of these are polar molecules, so both of them have PD-PD intermolecular forces. However, you guys know that chlorine has an electronegativity of 3.5 compared to, it's more electronegative than bromine basically. And sulfur and bromide, the crisscross relationship, like diagonally elements of the same electronegativity. So sulfur and bromine have almost the same electronegativity, but sulfur and chlorine have a greater difference, which is why the dipole is stronger, and this results in stronger PD-PD forces. All right. So let's write that down. I would just say that permanent dipole, permanent dipole forces in SCl2 are stronger, and we are going to explain why. Or you could just say that intermolecular force is stronger in SCl2. Why? Because SCl2 bond is more polar than SBr2. That's it. Or you could basically say that chlorine is more electronegative. Chlorine is more electronegative than Br. So SCl2 has stronger permanent dipoles. Fine, that's good. And there was an alternate for point one. I told you guys that intermolecular forces are stronger in SCl2, or the sum of instantaneous dipole attractions and permanent dipole attractions in SCl2 is greater than those in SBr2. Right? You could also say that. It's much longer, though. I prefer this. This just gets to the point, right? Bismuth is a dense metal in the same group as phosphorus. Draw a label diagram to show the bonding in bismuth metal. Okay, so it's basically you know, a metal. So cations in a sea of delocalized electrons. You know what? I'm just gonna copy this from the previous variant because they had the same question. So here you go. This is what you need to draw. You draw the at least four, right? You draw the ions and the delocalized electrons. And yeah, that's it. You've been doing this from all levels. By the way, sorry about the late uploads. I've just been busy with exams. I'm free for a month or so. Then I have exams again. So I'm going to try to upload as much as I can before the May-June 2023 session. Especially more paper 1, more paper 2, as well as paper 4. So let's see how it goes. Bismuth reacts with chlorine to form BiCl3. BiCl3 is a solid at room temperature. It melts when heated gently. BiCl3 reacts vigorously with water. So basically, since it reacts with water, it is a covalent compound. It is hydrolyzed by water, so it is covalent. If it was ionic, it would just dissolve in water. And it's solid at room temperature, but melts when heated gently. So yeah, it has covalent bonding, and the structure is honestly simple because when you heat it gently, it melts. If it was giant, it wouldn't melt so easily. Okay, so the bonding is covalent because it is hydrolyzed, and the structure is simple or molecular. Why though? Because it has a low melting point. Low melting point or boiling point. Okay, fine. That's good. Moving on to the last question then. This is organic chemistry. Let's do this. So yeah, how would we differentiate between these compounds? This is basically a ketone, propanone, and this is a 1, 2, 3 carbon aldehyde. So you know the test, right? This is propanal, and that's propanone. It's a methyl ketone. So basically, you could use Fellings or Tollens, or any oxidizing agent works because you can oxidize the aldehyde to carboxy acid. Or you could give aqueous alkaline iodine with A2. It would actually give a yellow PPT. Fine. So you have a bunch of options here. So I'm gonna write all of them if that's okay with you guys. The more you know. Tolerance, okay, gives us a. This is for A1, by the way. A1 gives silver mirror. Then we have Fillings. Okay, So A1 as usual gives brick red PPT. You could also go for K2CR2O7. So orange solution for A1. This is for A1. Okay, A1. Orange solution turns green, orange to green. Or you could go for dichromate. Do you guys see the color coding? KMNO4, A1, purple to colorless. Purple solution turns colorless. Fine. What about A2? A2 had another option. For A2, you could say that, you could basically add uh, alkaline iodine aqueous. A2 would actually gives yellow PPT. Okay, that is also an option for the first one. Fine. Now let's go to the next one. This is basically a ketone. It's a methyl ketone, and this is a pentan-3-one. It's not a methyl ketone, it's an ethyl ketone. So yeah, we have to use alkaline iodine aqueous. So this gives a positive result. B1 gives a yellow PPT, right? Yellow precipitate. CHI3 triadomethane. Then let's go to the next one. C2 is an ester while C1 is a ketone. So yeah, we can just use 2,4 DNPH, 2,4 dinitrophenylhydrazine. So C1 gives a red or orange. I personally prefer orange, or a yellow precipitate. Fine. What about D1 and D2? D2 has an alcohol as well as an alkene. D1 also has an alcohol. So yeah, you can just go for the test for unsaturation. We can add aqueous bromine. And yeah, the alcohol, the one with alkene, sorry, D2, turns it orange to colorless, right? Test for unsaturation. Orange to colorless. Fine. That's great. Amazing. Okay, so A1 and A2 are structure isomers. What is a structural isomer? Define structure isomer. Fine. So basically, structure isomers are molecules with the same molecular formula. That sounds so odd. Molecules with the same molecular formula and different structure formulae. Formulae. Okay, great. Yeah, I've seen this definition in the previous variant as well. Give the systematic name of B2. So B2, I just told you guys, it's a 1, 2, 3, 4, 5 carbon ketone. So that's pentanone. So specifically pentan 3-one. Yeah. Next, use the molecular formula of D1. So D1, what is this compound? This is CH2, CH2, CH2. There's a carbon over here. It has a CH3 attached and then OH. Okay, no H is over there though. So in total, we have 1, 2, 3, 4, 5 carbons, C5, 1 oxygen, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 hydrogen, C5H10O. Okay, C5H10O. Is that fine? Great. D2 forms polymer Z when heated gently. D2, it has an alkene, so it can clearly form an addition polymer. You only have addition polymers in AS, so yeah, it can't be condensation. Duh. So let's try to draw the compound D2. So this is D2, right? Um, Here you go. Okay. So let's draw one repeat unit. This is essentially CH2, CH, CH2, CH2OH, right? This is the compound. So if we draw the double bond first, just draw this double bond over here. Now there's gonna be two H's down here, right? So there's gonna be one H over here, and over here it's going to be CH, CH2, CH2, OH. And if you just remove the double bond, and open up the bonds on both sides. Here you go. That's that. Okay, that's one repeat unit. So I actually had this part done. I explained this before to somebody. So let's just do this blindly. Let's do this blindly. We don't have much left, right? It's almost done. So organic compounds E contains 3 carbon atoms. Fine. So it has 3 carbon atoms. It reacts with cold dilute KNO4. So obviously it has an alkene group, or else it wouldn't react with cold dilute KNO4. That is the specific reaction for alkenes. It forms a diol. Figure 3.1 shows the spectrum of E. Okay. Figure 3.2 shows the infrared spectrum of F. So guys, it's a 3 carbon compound. I know that for sure. And it has an alkene group like this. Now, I'm expecting that after it turns into a diol, when it turns into something like this, right? This, for example, we are going to get this broad peak on this side, right? Due to the hydroxyl group. Remember that you get a broad peak due to any form of hydrogen bonding, like in amines, then in amines, carboxylic acids, alcohols, etc. So yeah, this just proves that yeah, we just got an alcohol group. Okay, that's great. There's more details over here. So they want you to show that both spectra show absorptions between 2850 and 2950 for CH. Use the infrared spectra and table 3.2 to identify the functional group present only in E. Okay, only in E. Let's do that. So only in E, right? Wait, let me erase this. So something that's present only in E. I'm going to go with the CC double bond. Let's see why. I am highlighting this value over here. And the OH bond, right? Although the hydroxy one only, this one. So yeah, for alkene, what's special? If you think about it, 1500 to 1680, right? 1500 to 1680. Let's look for that. And we are supposed to get a strong peak, right? Oh, that's not given in the info anymore. Oh, wait, my pen isn't changing. As you can see, around 1500, there's this sharp peak, or this strong peak over here, right? So that is basically referring to your CC double bond, as I've told you before. So yeah, here we just opt for, one sec. It's just glitching out. Sorry about this. Yeah, here we just refer to the, you know, the bond at 1500, which is CC double bond, right? Wait. Okay, yeah. So it's just gonna be C double bond C, or just you could just write alkene, and the explanation is that there is an absorption at 1500 to 1680. Absorption at, or within, that's the word they prefer, within 1500 to 1680 per centimeter wave number, present in E. Present in E's IR spectrum only. Fine. Now about F, I just told you after K104 we get the diol, right? So with the 3200 to 3650, 3200, 300, like this part, this broad peak is for the hydroxy group. So yeah, I'm just gonna go for the functional group being hydroxyl or just alcohol, right? The explanation being there is a broad absorption. There is a broad absorption within 3200 to 3650 per centimeter present in F's IR spectrum only. Great. Now the mass spectrum of E shows a molecular N peak and an M plus 2 peak of approximately equal abundance. So guys, remember, the M plus 2 peak and M peak, we only have two in our syllabus. Chlorine and bromine. For chlorine, the ratio is going to be 3 is to 1, and for bromine, okay, the ratio is going to be 1 is to 1 because they're found equally in nature. So deduce the relative molecular mass of E. Let's try doing that. So how to do this? Essentially, the concept is this peak over here, 120. This is basically um the M peak, and 122 is the M plus 2 peak. Do we have other information over here? Yeah, we do. We knew that the MR of F is 154.9. The MR of F is 154.9. So this is E, this certain compound, and this is F with, two hydroxyl groups. So clearly there is presence of bromine in this compound, in our compound E. We know that compound E was a 3-carbon compound. We knew that for sure. Now we also knew that there was an alkene in the compound. Now since the M and M plus 2 peaks have equal height, we got another confirmation that basically there was a bromine in the compound. Now I don't really know where the bromine was. It might be on any carbon over here on the left hand side. Okay, but we just know for a fact that there's a bromine over here. It's something like this essentially. 3-carbon compound with an alkene, and let's check. Let's check. So basically, I'm saying that there's 3 carbons, 1, 2, 3. Now, what about the hydrogens? We have 1, 2 over here, 3, 4, 5, H5 and Br. Now, if you check the periodic table, so that's 3 times 12 plus 5 plus what's bromine specifically? 79.9, yeah? Let's check. 79.9, okay. 3 times 12 plus 5 plus 79.9, that's 120.9. Okay, great. Or you could just go for, 121, that's also fine. Do you guys get how I deduced it? Also, there was another way. You know that bromine exists in 50-50 ratio. So yeah, it would be 50% of 120 plus 50% of 122, right? That works as well. 0.5 into 122 plus 0.5 into 120 gives you an answer of 121. That was accepted as well, but this was the elite way, the way I did it. Anyway, use the information to suggest a structure for E. We already know that it's basically this compound over here, this 3-carbon compound, which is connected to bromine on the first carbon. I don't know why they picked the first carbon specifically. Oh yeah, wait, there's a logic behind this. No, the diol formation wouldn't be effective if the bromine was here. Honestly it wouldn't be affected because this isn't an alkyl group exactly. But yeah, you don't have to give the bromine over there. Like, your first thought should be it's at a carbon which isn't sp2 hybridized. It should be at an sp3 hybridized carbon. That should be the logic, probably. Anyway, whatever, let's try to complete this equation. So we had a c5h sorry, c3h5br, or this compound basically, ch2 CH2Br. So what happened was, this was oxidized. It formed this diol over here, CHOH CH2Br. Now, how did this happen really? So C3H5Br. It was with the help of nascent oxygen. Okay, and no hydrogen was lost really. Rather, no hydrogen was lost, rather it was added. How many hydrogen atoms? Look, 2 hydrogen atoms and 2 oxygens were added. So out of that, 1 oxygen atom and 2 hydrogen atoms are coming from water, and the other nascent oxygen is providing the second one. So we get this compound C3H7 and O2. That's the compound we get. See if that makes sense. That's how we got this diol. Now C2 can be synthesized using A1 as a single organic reagent. So what is A1? It's basically a 3 carbon aldehyde or propanol. And what is this compound over here? C2. It's a 1 2 3 1 2 3. It's a 6 carbon carboxylic acid, propyl propanoate. So you have propanol, right? So propanol is an aldehyde. You can convert propanol to propanoic acid by oxidizing it, and you can reduce propanol to get propan-1-ol. Then you can undergo, it can undergo esterification, propan-1-ol and propanoic acid to form propyl propanoate. So that is the logic. All right. So let's do this. So for one portion of A1, what are we gonna do? We are going to reduce it using NaBH4 or LiLH4. Anyone works? Reduction to propan-1-ol, which is CH3, CH2, CH2OH. Fine. So second portion, what's going to happen essentially? We are going to oxidize it, right? What's our choice? Esterified dichromate K2Cr2O7. Oxidation to propanoic acid CH3CH2COH, right? Propanoic acid. Fine. Awesome. Now, what are we going to do with both of them? Esterification with the help of a few drops of concentrated H2SO4. So the two products, we are going to use concentrated H2SO4 specifically. Okay, just write H2SO4. This is the best answer as catalyst for esterification. All right, that's it. So guys, yeah, that's the end of the paper. We've reached the end. If you do have any queries, please feel free to comment below. I am going to link the paper for October, November 2022, paper 2.1 or 2.3 up here, and the playlist for chemistry, paper 2 up here, and my video for AS organic chemistry. You guys can check that out for a quick review, and remember to subscribe to the channel if you like the content. See you guys later. Bye.